Welcome back. We're now going to talk about how we actually use those equilibrium constants, the Ka constant. And if you remember, Ka should make you immediately think of Ha aqueous goes in equilibrium with H plus aqueous and A minus aqueous. Right? So we're always looking at that relationship when we're talking about H plus or HA, and we're talking about Ka expressions. So if our acid was HF, right, our A would be the F. If our acid was acetic acid, C2H3O2, our A would be C2H3O2, and at the end we'd have C2H3O2 A minus. Okay. Now, since this is equilibrium, we said, hey, we're just going to use ice tables to solve all these kind of things, but we have to be aware of one more thing. In water, we can have an acid producing H+, but we also just figured out that water can auto-ionize into H3O+, which again is the same thing as H-, as H+. So we've got water auto-ionizing, and we've got two things producing H+ in solution. So how do we figure out how two things contributed H+ in solution simultaneously? And the answer is we have to look at how much they're each contributing. Now let's take something like HF, for example. If we looked up HF, it has a Ka value of 7.2 times 10 to the minus fourth. And if you remember, the Kw value for water is 1 times 10 to the minus 14th. And what we learned when we looked at those Ks originally is that a very large K means we favor our products. A very small K means we favor our reactants. So here we've got K values that are different by 10 orders of magnitude. The K for the equilibrium of water dissociating is 10 orders of magnitude less than that of HF. So which one do you think is going to contribute a lot more H+ to the solution? Right, the one with a 10 orders of magnitude greater K, right? It's going to contribute a lot more H+. And so what we're going to find is that as long as our Ka values are relatively large, now what is relatively large? 10 to the minus 11th, 10 to the minus 10th, 9, 8, 7, 6, 5. Those are much larger than 10 to the minus 14th. And we're going to be able to just completely ignore the contribution of water from those. In the cases where we have K smaller than that, we won't run across that in this class pretty much. What you actually have to do is take into account both. And there's ways you can do that that are kind of fun and involve successive approximations and all sorts of things. But we won't get into that too much. So we're going to ignore water. We're going to ignore that contribution, which does make this essentially an equilibrium expression with an ice table. So we have to think of our two situations. Remember, we had strong acids and we had weak acids. Do you remember your strong acids? HCl, HBr, HI, HNO3, H2SO4, HClO4. So let's say we had HClO4 and it was 0.200 molar and we wanted to know what is my pH. It might be tempting if you just look at this, be like, okay, I've got an acid there, I need to bump my ice table because we were talking about that, but you have to know that HClO4 is a strong acid. So HClO4 at 0.2 molar is going to produce 0.2 molar H+. Because 100% of it's going to dissociate. Thinking in terms of atoms, right? If I had two molecules of HClO4 and they completely dissociate, I'm going to form 2 molecules of H+. 2 moles of HClO4 is going to give me 2 moles of H+. 0.2 molar HClO4 is going to give me 0.200 molar H+. And my pH is just going to be the negative log of that, negative log of 0.200, which is 0.6. Let's see, how many significant figures do we have? 0.699. Right? So we can determine the pH of solutions very, very simply. Right? If it was 10 to the minus 2, our pH would be 2. 10 to the minus 3, our pH would be 3. When we have strong acids, very, very simple. But now in the case of a weak acid, it does become a little bit harder, and this is where we have to bring in our knowledge of equilibrium. So let's go ahead and do HF, just because we already looked at its equilibrium constant. And so we're going to say we have a solution of 0.010 molar HF, and we want to know what is the pH. Okay. Now, it's tempting if you're not paying attention to be like, okay, I just did that other thing. Let me just take the negative log of 0.01 and my pH is going to be 2. And that would be the case if it was a strong acid, but it's not a strong acid. So you need to know your strong acids to make sure you understand when you have a weak one. But we know this is weak, and we know that its Ka value is what I said, which was 7.2 times 10 to the minus 4th. All right, so what do? Now we do our ice table. So we're going to have our standard here, HF goes to H plus and F minus. Our ice table is going to look like this. We start with 0.010 of this. We don't start with any fluoride ion. And it's very tempting to write a 0 here because you're like, well, I didn't put any H plus yet. But remember, this is happening in water. We decided earlier that we can probably ignore the contribution of water. But what I like to do is I like to remind myself that there is H plus from water in there. So I don't generally write 0 here. I usually write approximately 0. And in cases where I might need to consider the contribution of water, I could actually write water's 1 times 10 to the minus 7th, what it contributes. We won't do that too much, but we'll see a couple examples maybe later on. What's going to happen? Well, if we have no products, we know our reaction is going to go to the right. We're going to form x of this, minus x of this, since we get 0.010 minus x, x, x. We know our Ka expression is going to be H plus times F minus over HF, and that's going to be x times x over 0.010 minus x. And that's going to be our Ka value, which was 7.2 times 10 to the minus 4th. All right, what do? Let's try the small x assumption. We're a little on the edge there. So it's 7.2 times 10 to the minus 4th compared to 0.01, 2 orders of magnitude. We usually aim for 3 orders of magnitude or more. So maybe let's not make a small x assumption, right? It's hard. Sometimes I just want to make it because it's so much easier to do. But, you know, really 2 orders of magnitude is probably not enough. In fact, that 7.2 times 10 to the minus 4th is actually pretty close to 10 to the minus 3rd. And so really we probably can't make the small x assumption. So we actually just have to solve this one exactly, right? We get our x squared is equal to 7.2 times 10 to the minus 4th times 0.010 minus x. And then we have to multiply all of that out. I'm not going to show you all the work for this one. Hopefully you can do the work for this one, do the quadratic formula. We've had some experience with that from the equilibrium chapter. I'm just going to tell you that we get 2 roots that one of them doesn't make sense because you end up with a negative value. But the root that does make sense is going to be our x, and it's going to be our H plus concentration, which is 0.00235 molar. Our pH is just going to be the negative log of that, of 0.00235. And if you do that in your calculator, you're going to get 2.629. What's our sig figs like? When we're doing sig figs on this one, we always have to look in 2 different places. What were the significant figures in our concentrations? What were the significant figures in our K value? 90% of the time, we're going to be limited by our K value. So here we've got 2 significant figures in our K value, which means we only get 2 digits after the decimal there. So this is going to be 2.63 as our pH. And I don't believe I emphasized it earlier. pH has no units, right? So we don't hit any units on that. 2.63. What would it have been if it was a strong acid, right? It would have been a pH of 2. Negative log of 0.01 is 2. So we get a higher pH. What does higher pH mean? Higher pH means less H+. We're closer to neutral than we are if this was a strong acid. And so we're going to find that. Weak acids are always going to have a higher pH than the equivalent concentration of strong acid. All right. Which brings us to your turn already. Now that we know how to set these things up, you should be able to set up our reaction, right? You see, hey, look, I've got a Ka. I know that's going to be Ha goes to H plus plus A minus. You write out that reaction, you do your ice table, and you can make the small x assumption in this one. Why? Because you've got a 10 to the minus 9th here compared to 0.3. That's 8 orders of magnitude difference. You're fine. Okay. So go ahead and make the small x assumption, and then and then see what you get. My mind just turned off for a moment. Go! What'd you do? You want me to go through it? I can go through it. Okay, hyperbromous acid, HBRO. Okay. BRO minus ICE. We've got 0.300 molar. 0? Approximately 0. 0. And what do? Minus, we get plus x here, minus x here. That was silly. I don't know why I did that. Minus x here, plus x here, plus x here. And so we get 0.300 minus x, x, x. You're like, hey, that looks a lot like our last ice table. Yeah, these ice tables, they're all identical. They're all almost entirely identical. You end up with Ka equals H plus times BRO minus over HBRO, and you end up with x squared over 0.300 minus x, and you're going to see that over and over again. Does that mean you don't have to write it out? No, because you're just learning this stuff, so I want you to practice it. I want you to practice these ice tables, get them down so that you can do them like that, right? Then, you know, after you leave this class, if you ever need to do it again, you're like, okay, I got the ice table down, I can do it whatever, and I can use some of these shorthands that you might see on the internet. But when you're doing it for my class, I want to see the ice table every time. So what are we going to do? We're going to find that Ka value, which was given in our problem as 2.8 times 10 to the minus 9. We decided we can use the small x assumption because there's a big difference between our Ka and our concentrations. So we're going to say it small x. Always state our assumption explicitly. And so we end up with x squared is equal to, over 0.3, because we're ignoring the x there, is 2.8 times 10 to the minus 9th. And so we get x squared equals 0.300 times 2.8 times 10 to the minus 9th. And you take the square root of both sides, and you go ahead and you find that x is equal to 2.898 times 10 to the minus 5th. That's my concentration of H+. I'm looking for pH, so I'm going to take the negative log of 2.989 times 10 to the minus 5th. And what do I get if I take the negative log of that? I get 4.54. Significant figures, most always from our K. Our K has two significant figures, so we have 2 digits after the decimal in our pH. So 4.54, hopefully you got A. There's a lot of work. There's a lot of steps in these problems, but there's a lot of similarity in them too. So when you get used to it, you can go through them pretty quickly and pretty regularly. All right. So the other thing we can do is we can measure pH in order to find a Ka. So here, so far, we've been using our Ka in order to find pH, but how do we find those Ka values? Well, one way they do it is by making these solutions, measuring the H+ concentration, measuring the pH, and using that to find Ka. So we're going to use HOCl in our example here, and we're going to use H+ plus OCl minus. We're going to go ahead and start with a solution of 0.100 molar this. We don't know what the Ka value is. We're trying to figure out what it is, but we know we started off with approximately no H+, no OCl minus, and so we can go ahead and make an ice table for this. There's nothing stopping us from making an ice table. It's going to look exactly like the rest of our ice tables, 100 minus x, 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 and we can write our Ka expression is going to be H+ times OCl minus over HOCl. And when we plug it in, you get x squared over 0.100 minus x. But the problem is we don't know the Ka, so we can't solve for x. So what did I say we do? We go out and we make this solution. We put in the 0.1 molar HOCl. We measure the pH, measured pH, and that is a value of 4.23. Now, how does that help us? Well, what is the pH related to? It's related to the H+ concentration. And the H+ concentration is related to x. And so I can actually figure out x, because it's the H+ concentration, is 10 to the minus pH, or 10 to the minus 4.23, which is a 10 to the minus 4.23 is 5.89 times 10 to the minus 5th. So now we know x. If we know x, we can plug it into our expression here. We know that Ka is x squared, so 5.89 times 10 to the minus 5th squared over 0.100 minus 5.89 times 10 to the minus fifth. And we have that. We do it just like that, and we calculate our Ka value is 3.47 times 10 to the minus eighth. What's our significant figures? Our pH had 2 digits after the decimal, so we are certainly limited to 2 significant figures, and we're going to call this a 3.5 times 10 to the minus eighth. So we can use our Ka to find a pH, if that's what we want. We can also use a pH to find a Ka value, if that's what we're looking for. So lots of different things we can do with this kind of work. All right, the last thing we're going to cover in this chapter is if we know how much it dissociates, right? We can figure out that from an ice table. It turns out that sometimes that's a useful number to know. Oh, how much of this dissociated? How much of my weak acid turned into H plus the A minus? And we define that as the percent ionization. And it's got a very easy definition, very simple definition, and it's just this. The percent ionization of any weak acid is the concentration of A minus at equilibrium. So after you've solved it in your E line on your ice table, divided by the concentration of HA that you started with. That 0 there, that sub-zero means initial concentration. HA naught is what we call it. And then you times by that 100% in order to get a percent value. So we're going to go ahead and do that. We're going to practice it for acetic acid. We're going to start off with 1.00 molar acetic acid. And what I want to know is what is the percent ionization? Okay, that's what we're going to do. So acetic acid is HC2H3O2. We're going to run across acetic acid a lot, and so a shorthand that people will often do is HAC. So if you see HAC, chances are people are talking about acetic acid. And I'm going to go ahead and use that shorthand just because it saves us a little bit of time. So I've got HAC goes to H plus AC minus, and I'm going to do my ice table. ICE 1.00 molar, approximately 0.0 x 1, oops, sorry, minus x here, 1.00 minus x. You getting tired of these ice tables yet? A lot of similarities, very, very similar every time. We've got our Ka is equal to concentration of H plus, concentration of AC minus over the concentration of HAC, which is going to be x squared over 1.00 minus x. I didn't give you a K value yet, but the K value is 1.8 times 10 to the minus fifth. We are good for the small x assumption. I just realized something. On the last problem, I forgot to check my assumption. It turns out it's very good, but ooh, I lost some points on a test or quiz because I didn't check my assumption. You have to check your assumption every time. If you make the small x assumption, you must check it. Okay? So I lost some points there. Don't you lose points on your quizzes either. But it's really easy, right? You're moving along, got answer, done. But part of your answer is your answer reasonable? And one of the ways you have to verify that your answer is reasonable was your assumption reasonable? We'll do that this time. We'll make sure to check our assumption. Okay, so always state your assumption. Don't just do it. Say, I'm going to make the small x assumption. I get x squared over 1.00 is equal to 1.8 times 10 to the minus fifth. And I get that x equals 1.8 times 10 to the minus fifth square rooted, which is 4.2 times 10 to the minus third. Right, and that is my AC minus concentration from my equilibrium table if you look back at your notes. So I've got AC minus there, and if I want to find the percent ionization, it's just going to be my AC minus concentration, 4.2 times 10 to the minus third molar, divided by my initial concentration, which is 1.00 molar. That was my initial acid concentration, times 100%. And so what do I get? I get 0.42% ionization. So acetic acid is a somewhat strongish weak acid, and still only 0.4% of it dissociates, right? Which means 99.6% of it stays as acetic acid, and only 0.4% of it turns into H plus and AC minus. But that's how we calculate our percent ionizations. Okay. Now, what would happen if you raised up your concentration of acetic acid. So I'm not going to do all this work again. I'm just going to show you what happens if we changed our acetic acid concentration to 2.0 molar. So the only thing that would change down here is 2.0. Now, you're like, Professor Clements, do you know what you forgot to do? What did I forget to do? It's easy to forget to do it. I forgot to check my assumption. Let's check it. Okay, x is 4.2 times 10 to the minus third. We're going to compare that to 1. 4.2 times 10 to the minus third compared to 1.00. Hey, look, that looks an awful lot like our answer for percent ionization. So that is 0.42%. That is good. We're less than 5%. So good assumption. Always good to write that down. Write down that you assumed small x. Write down that you checked it. Good assumption. Those are required things in your solutions. So we're going to take x squared divided by 2.0 equals 1.8 times 10 to the minus fifth mole, or as our k value. I'm going to go ahead and solve for that by taking the square root of 2 times 1.8 times 10 to the minus fifth. And I get 6x equals 6 times 10 to the minus third. And I compare 6.0 times 10 to the minus third molar compared to 2.00 molar. And what do I get? Divided by 2, and then times 100 to get percent, and I get 0.30% ionization. So as I increase my concentration of my acid, right, what do I find? I find that my percent ionization decreases. Okay, so that's something to be aware of. As you add more and more acid, you don't actually get increasing percent ionization, you get decreasing percent ionization. One way to think about that is kind of a Le Chatelier's thing. To get to 1 molar, right, I put in a bunch of extra H+, right, 0.42% of it dissociated. That H+, when I add that from 1 molar to 2 molar, right, so I added another 1 molar, but that H+ is now acting as the Le Chatelier kind of thing, which is driving my reaction back towards the left. It's not a perfect analogy, but it does kind of work. But just be aware of that as my concentration of acid increases, my percent ionization decreases. That is it for this particular section. Hope you learned something about percent ionization, about making calculations using the Ka expression. It's again just our ice tables, our equilibrium stuff. They all look very, very similar. So you're going to see the same thing over and over again. You're going to get pretty sick and tired of it, but that's good. When you get sick and tired of something, it means that you recognize you're doing the same thing over and over again, and you actually understand those type of problems. So great. Thanks for listening, and have a wonderful day.